So continuing on with motion. Yesterday we talked a bit about the motion diagrams. We talked about a little bit about in terms of graphs. If we have a graph of position versus time, there's a few things we can determine from that graph. For example, we can figure out where we started, the initial position. So with this initial point being below the origin, that means we started on the negative side of our origin. But we're walking closer and closer until we get to the origin, but we continue walking through and continue onwards until we end up this far from the origin. So it would be like starting over here and walking this way until we reached some maximum distance from our origin. With the line being straight like this, we know we're covering the same amount of distance in the same amount of time. So that means we're walking at a uniform rate. This would be uniform motion. By that we mean we have a constant velocity. We're moving in a straight line. We're moving at a constant speed. We're not walking faster or slower at all during those times. What does that tell us about the acceleration then?
Zero.
It's zero. If your velocity is not changing, then you can't have any acceleration. Exactly right. Now velocity. If I have a graph like this, how would I find the velocity? I mean, it's nice to know it's constant, but what would we need to know in order to actually find the numerical value of it?
Amount of distance in time.
So let's say this is negative 10 meters. That's positive 15 meters. We've taken a total of 3 seconds to move that. Graphically, what is the velocity?
Slope.
The slope. Exactly right. The velocity would be our change in position over change in time, since the acceleration is zero. The velocity is always the slope of your graph. In this particular case, we have a constant slope, which is why we know we have a constant velocity. Okay? Constant slope, the change in position, well, our final position is 15 meters, minus our initial position, which is negative 10 meters. Change in time is 3 seconds. So we have 15 minus a negative 10, which is 25, over 3. So 25 over 3, 8 point something, 8.3 meters per second. Now, it's 8.3 meters per second is just the speed. That's the magnitude. What about the direction? In this case, positive is enough right now. Since we're just dealing straight line motion, positive and negative is all we're going to use to distinguish our directions. If you wanted, you could say to the right in this situation. So our velocity is simply the slope of our graph. If we want instantaneous velocity, in this particular case, the instantaneous velocity at any point is 8.3 meters per second, because our slope is constant. It's not changing. So the value of the velocity is always 8.3 meters per second. But if we had, say, something like that, the velocity is not going to be constant. In fact, it's starting quite large. It's getting smaller and smaller and smaller and smaller. At that instant, it's zero. Then it's getting bigger and bigger and bigger and bigger as it falls back down. The slope is positive on this side. The slope is negative on this side. So that means the velocity is positive for the first half of the motion. The velocity is negative for the second half of the motion. So if we were to graph velocity versus time, it would be roughly, we start out at a relatively large positive value. So we would start out at a relatively large positive value. The velocity is getting smaller and smaller and smaller and smaller until it eventually, at this instant, is 0. Because the slope would be 0 if we drew a tangent line at that point. But then it becomes negative and becomes bigger and bigger and bigger. That would be our velocity. Starts big positive, it's positive, 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 but getting smaller and smaller in magnitude. It's 0 at that one instant. It's now negative, getting bigger and bigger, more and more negative.
That's graphing the derivative of the other graph.
Exactly. Velocity is the derivative of position. So the derivative, remember, is just the slope of a line tangent to the graph. So yes, velocity is the derivative of the position with respect to time. Acceleration is the derivative of the velocity with respect to time. What can you tell me about the acceleration in a situation like this? Constant and positive or negative? Negative. So it's a constant negative value. The slope of the velocity graph is negative. So this actually would be representative of what? Give me a real life example.
Something going up and coming down.
Sure, exactly. So throwing a ball up, as long as we're looking at the instant after it leaves our hand. So we throw it, once it leaves our hand, it's moving relatively fast, but it's going to go slower and slower and slower until it reaches 0, and then it'll speed back up on the way back down. Exactly right. Fabulous. So let's say we had a function that described a graph similar to that. Let's say the position of our ball, for example, was described by this function, 5t minus 4.9t squared. By the way, the 5 has to have units of what? Meters per second. Position is a distance. It needs to have units typically of meters. This term needs to have units of meters. Time is typically in seconds. So the 5 has to have units of meters per second, so that when we multiply by the number of seconds, we get meters. What about the 4.9? Meters per second squared. Exactly right. Very good. So if that is our equation describing the motion of our ball, what will the equation describing the velocity of our ball be?
5 minus 9.8 t.
Yes, so the derivative, we get 5 minus 9.8 t. The 5 still has units of meters per second. This term here, it's now 9.8, but it came from the 4.9, so it still has units of meters per second squared. The units stay with it. The acceleration.
Negative 9.8.
Exactly. Negative 9.8. And again, it still has the units of meters per second squared. In this case, it's not changing with time. In this particular case, it's constant. So when we're in terms of units, we typically use kilograms for masses, meters for distances, seconds for time, Anything else? So that means velocities will be in meters per second, accelerations will be in meters per second squared. Okay. Those are the SI units, the International System of Units, that we use in physics. What if just making something up. Let's say we have an object that is moving and its velocity can be described by this equation, 4t minus 3t squared. How far will the object move in the first 10 seconds of its motion? So between time equals 0 and time equals 10 seconds, how far will this object move? Well, velocity, we know. We could certainly find the velocity at any point in time by plugging the time in. But how can we get to some sort of position from velocity? Integrate, antiderivative. Either way, yes. So x, the position, will equal the integral of 4t minus 3t squared with respect to time. We're integrating with respect to time being our variable. What do I do about the 10 seconds? Those are our limits. Our lower limit is our starting time. Our upper limit is our ending time. So those determine the limits, which we'll plug in at the end. Integral of 4t squared over 2. Integral of 3t squared will be 3t cubed over 3. So basically 2t squared minus t cubed. Plugging in our limits from 0 to 10 seconds. Remember, when you have limits on your integral, you don't have a plus c when you do the integration. The only time you plus c is if you don't have limits. So here we get 2 times 10 seconds squared minus 10 seconds cubed. Plugging in 0, we're going to get 0. So let's see, 200 minus 1,000. So negative 800. Now the units. Let's go back to the beginning here. Sorry, this was the beginning. The 4 has to have units in order for this equation to work properly. This equation is describing a velocity. What units should velocity have? So that means this term needs to give us meters per second, and this term needs to give us meters per second. So the 4 has to have units of meters per second squared, so that when you plug in a certain number of seconds, one of them cancels and leaves us with meters per second. What about this one? Meters per second cubed. Those units are still here. This still has units of meters per second squared. The second term still has units of meters per second cubed. The units are still there. So when we take meters per second squared times second squared, we get meters. When we take our meters per second cubed times seconds cubed, we get meters. So our answer is in meters.
And that's different from the distance traveled, correct?
This is where how far it will start off from wherever it's. This is basically its displacement.
How far it would be
Yes,
displacement.
from where it started.
Is that